Okay, so we want to demonstrate the phenomenon of total internal reflection here. We've got light from a ray box, which is traveling into a glass wedge, and then emerging here into the air. So the air on this side is less dense than the glass on this side. So we just want to vary the angle of incidence here from the ray box. Now we can see that the angle of incidence here inside the glass is smaller than the angle of refraction in the air. So we've got an angle there of about 30 degrees in the glass, and then over here in the air it's about 50 degrees. So the angle of incidence is clearly smaller than the angle of refraction. As we increase the angle of incidence further, we can see that the light ray, the angle of refraction measured from the imaginary normal line over here, is getting closer and closer to 90 degrees. And we'll reach a certain point where the ray essentially is about to disappear. So right now the angle of refraction is 90 degrees. Measured from this imaginary normal, we've got a 90-degree angle there. We also see interesting effects there where the light is actually being split up into its constituent colors. That's a phenomenon known as dispersion, and there's a slightly different index of refraction for red light than there is for blue light. We also notice over here that the reflection line has gotten quite strong. That's simply because most of the wave energy is now being reflected and very little is being transmitted onto the other side. If we increase the angle of incidence just a little bit more, the refracted ray totally disappears, and now all of the light is internally reflected inside the glass. So we're shooting light at a transparent boundary, and most of it is bouncing back. Virtually all of it is bouncing back. That's total internal reflection. We can demonstrate that over here as well. Here we have just a little tank filled with water, and we've got a laser that will shine into the water here. So here you can see the angle of incidence. It's about 20 degrees from the normal, 25 degrees from the normal in the water, and it's about 50 degrees out in the air. So once again, the angle of refraction is greater than the angle of incidence. As I increase the angle of incidence, notice that the laser light, the refracted ray, is now at about a 60-degree angle, and I'll increase it still further, and now we're up about 70 degrees, and right around here in the mid-40s, once again, the refracted ray totally disappears and all the energy is reflected. That's total internal reflection. So this is light coming from water, hitting the transparent surface of the water, and all of it is bouncing back. There's no refracted wave at this point. That's total internal reflection. Okay, so let's study this mathematically. When light goes from a less dense substance, say like air, into glass, then it bends towards the normal. So if this ray is here in the air, then when it goes into the glass, it will have a smaller angle of incidence. It'll be smaller than, the angle will be smaller than it was in the air. So we measure angles with respect to an imaginary normal line. Here's that imaginary normal line here. And so this substance here is air, and then this substance down here is glass. So the angle in the air is larger than the angle in the glass. It bends towards the normal line. Now, if we reverse that experiment, so now we're sending a ray from the glass out into the air, what we find there is that the angle actually increases. It bends away from the normal line. And the normal line, again, is just this imaginary line perpendicular to the interface. So the light ray bends away from the normal line when it's going from something more dense to something less dense. Now, clearly, the angle of refraction can only get to 90 degrees. So in that experiment we just did, if we're going from something that is more dense to something that is less dense, we'll reach a point where our light ray in the glass is now bending and going along the interface in the air. And that is something known as the critical angle. because if we increase this angle even a little bit more, this refracted ray will totally disappear. So right now it's 90 degrees. This is in the less dense medium air, this is in the more dense medium glass, and this is the critical angle. And if we increase any more the angle of incidence, this ray will totally disappear. And then all of the wave energy will be reflected. Now I didn't draw the reflected ray here. Let's just add it in. It's relatively faint until you reach this condition here of total internal reflection. Now of course by the reflection law, the angle of incidence should equal the angle of reflection. So just let me draw that one. This will also be theta critical. And you really start to notice an increase in the intensity of the reflection as you get close to the critical angle. And beyond the critical angle, you do have total internal reflection. And this, of course, is the principle of fiber optics, where you shoot light down a glass fiber and it stays inside the glass fiber. Let us derive an expression then for the critical angle for water, assuming that the light ray is heading out into air. Okay, so here's the imaginary normal line, and then we're shooting a ray of light here from inside the water, and this is our angle of incidence theta 1, and this is water. And then at the critical angle, we're about to lose our refracted ray. Our angle outside here is 90 degrees. So we apply Snell's law, which says N1, sorry, the way we write it is a little different from that. Let me clean that up. The way we wrote it in class was to say that speed was larger when wavelength was larger, when angle was larger, and that happens when n is smaller. So speed and wavelength are in proportion to angle and inversely in proportional to the index of refraction. So if we rearrange that, then we could say that n1 sine theta 1 is n2 sine theta 2. So this is actually in the water. This is the incident ray in the water, and then this is the refracted ray in air. The index of refraction for water is 1.33, and it's this angle that we're looking for. The index of refraction in air is 1, and at the critical angle, the angle of refraction is 90 degrees. So we solve. Sine of 90 is 1, and then the critical angle in water will just be the inverse sine of 1 divided by 1.33, and then we will do the inverse sine, and we see that's 48.8 degrees. And that's about what we saw in our demonstration. Remember, somewhere in the mid-40s to almost 50, we were losing our refracted ray, and we were seeing total internal reflection.